Hello, 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 and welcome. If you're watching this, you missed day 1 of our week 14 lecture, and we're talking about catapults. So let's get to it. We've got 2 assignments. One is due tonight at midnight, so if you missed it, you need to do this ASAP, please. And that is the catapult warm-up. I'll show it to you in a second. The second one is due Friday the 4th, and is the catapult checkpoint 1. Now our objectives are that you can begin planning for the catapult project, which is what this is going to be right here. Identify required qualities in a catapult to make it as good as you can. And identify 3 laws of motion, which I think is something we haven't quite touched on, but is important to really understanding the physics behind what you're doing here. So let's take a look at some constraints for our actual catapult. These are some examples of designs you could go for. These are certainly not the only designs, just getting you in the mood. Now, your catapult is an individual project, must be constructed out of popsicle sticks primarily. So you can use other materials, but I shouldn't see like a Lego catapult with 1 popsicle stick in it. I should see a popsicle stick catapult with some Legos in it, if you're going to use Legos, or whatever other materials you want to use, but primarily popsicle sticks as the structure. All right. Must use a crumpled up ball of paper or note card as your ammunition. This is to make a level playing field for everybody, so no one's shooting with like a marble, which would obviously go much, much farther. So we're all using the same thing. May not be fired at a living thing and should strive to reach the farthest distance possible. So we're trying to shoot far in this particular exercise. The whole point is to get as far away from the catapult as you can with your projectile. 3 more things to consider. Catapult must fit into an 8 by 8 inch space. So how do we do that? Well, if you take a standard piece of paper, the short side of it is 8 inches. So 8 by 8 by 8. 8 in every direction. So think of it like a cubic space. Shouldn't be too hard. We don't want it to be too big. And catapult must be freestanding, so you can't be holding it up with your hands. It's got to stand on its own when you go to fire it. Must have an adjustable aim. And you can achieve this in 2 ways. You can either change the angle of launch or the power of launch, or both. So how do we do that? Well, if we take a look at this example over here, let's say we look at this catapult on the left. To change the power of launch, we can either change how far back we pull our lever before we launch. We can change how many rubber bands attached to the bottom here. That would give us more power as well. We could change the length of our lever. To change the angle, we can do something like stop the lever at a different point. So put something behind this crossbar to stop the lever arm sooner. Or we can change the length of the bar. Notice that changes both the angle and the power. So that one will have different results depending on what you do. As long as you have sufficient power, it should increase the distance. But if you don't have enough power to make that longer lever arm worth it, so to say, then you're actually going to see worse results. Now let's talk about Newton's 3 laws of motion. This is not something we've covered yet, but is probably the central idea behind launching anything, really, into space, right? And by this space, I mean any space, not necessarily space that's in space, if that made any sense at all. So, every object persists in its state of rest or uniform motion in a straight line unless it's compelled to change that state by forces impressed on it. That's a lot of gobbledygook, but all it's trying to say is an object that's already moving in a particular direction wants to keep doing the same thing. If it's not moving, it's going to stay not moving. If it's moving somewhere, it's going to stay moving. Now, gravity changes that. That's a force that's affecting it. But if there was no gravity, nothing in the way, nothing to hit, an object would just keep moving the same way it was all along, forever. Force is equal to momentum, to change in momentum per change in time. So for a constant mass, it's mass times acceleration. This second law, all you need to kind of get from it is this formula, F equals ma, something we take for granted oftentimes, but it's really crucial to understanding any kind of force, right? It's just a mass times its acceleration. Very powerful stuff. For every action, there's an equal and opposite reaction is the third law. and that one is self-explanatory. I don't think I can add anything to that to make it clearer. If I push down on the table pushes back on me, so we have the same amount of force going back into my hand as I apply to the table. All right, now there's a couple of assignments for you guys to do, so let's take a look at them together. So if you go to modules on my MCPS, you'll see that there are 2 assignments posted here. The first one is the warm-up. The warm-up is very, very straightforward. You just need to read through the short article right here and answer the questions below. Shouldn't take you super long. The questions are very straightforward. This is 4 points for participation. The second assignment is the longer one, is due Friday. It involves a little bit of research on your part, so it's going to be a little more involved. What you have to do here is you have to look through and write the description of your problem. So state what you're trying to achieve with your machine. What is it trying to do? How will you know you're successful? That's what you put here. Next, you list at least 4 criterion constraints. You can refer back to the PowerPoint for those. What is a catapult in your own words? Describe 6 simple machines. Remember, we've covered this extensively last week, so you should know what simple machines are. Describe the 3 laws of motion. I just did that for you, but you can certainly put this in your own words. Define velocity, potential energy, projectile. And last but not least, make sure you don't forget any of your sources. List them here. And the last part here, you have to look for 3 siege machines from the Middle Ages, get their pictures, and figure out what is the power that makes the projectile launch. Is it a rubber band? Is it spring? Wood being bent? What is it? How does it work? Write a short explanation of the power source that makes the machine throw whatever it's throwing, not necessarily a rock. The last one, you're going to do the same thing, but now you're looking for student-built projects, so other projects that people somewhere else in a different school have done that you can draw inspiration from. So what is the power source? Does it adjust for aiming? Does it have a trigger? Obviously, you might not find a catapult that fits exactly the criteria we're using, but any kind of catapult that student made could have things you could borrow, even if the catapult itself might be very different from what we're making. So it's fine if these aren't exactly to our specifications, so long as you can draw something away from what they're doing and it's helpful to you. If you have any questions, please reach out to me or come see me on Wednesday. Again, I'm available from 9:30 until 2:30 every single Wednesday. Otherwise, have a fantastic rest of your day, and I'll see you guys later.